Welcome to this interactive study guide on energy changes in chemical reactions. Every reaction involves energy transfer. Energy is never created or destroyed, only moved between the reacting chemicals and their surroundings. Understanding whether a reaction releases heat, exothermic, or absorbs heat, endothermic, is crucial not just for passing your exams, but for real-world applications like hand warmers, sports injury packs, and hydrogen fuel cells. In this video, we'll break down the key concepts: exothermic and endothermic reactions, reaction profiles, activation energy, and bond energy calculations. Let's dive in and secure those marks. Let's map out the core concepts. Exothermic reactions transfer energy to the surroundings, so the temperature rises. Endothermic reactions take in energy, so the temperature falls. Every reaction needs a minimum amount of energy to get started, that's the activation energy. Reaction profiles are graphs that show the relative energies of reactants and products, along with the activation energy hump and the overall energy change. Understanding these diagrams is a key skill for your exam. Now let's look at the essential process behind energy changes. In any chemical reaction, old bonds in the reactants must be broken, and new bonds in the products are formed. Breaking bonds requires energy, so it is endothermic. Forming bonds releases energy, so it is exothermic. The overall energy change of the reaction is the difference between the energy absorbed to break bonds and the energy released when new bonds form. If more energy is released than absorbed, the reaction is exothermic. If more energy is absorbed, it is endothermic. For example, combustion of methane releases a lot of heat because the energy released in forming carbon dioxide and water is greater than the energy needed to break the bonds in methane and oxygen. Let's go through the process step by step. First, the reactant particles collide with enough energy to overcome the activation energy. Bonds in the reactants break, absorbing energy from the surroundings. This makes the surroundings feel cooler initially, but it's only temporary. Then atoms rearrange and new bonds form, releasing energy. The net effect on the surroundings is the overall energy change. In an exothermic reaction, more energy is released than absorbed, so the surroundings heat up. In an endothermic reaction, more energy is absorbed than released, so the surroundings cool down. This is the fundamental principle that ties together all the concepts. Let's work through a typical exam question on bond energy calculations. The reaction is hydrogen plus chlorine to form hydrogen chloride. First, identify the bonds broken, one H-H bond and one Cl-Cl bond. Add their bond energies, 436 plus 243 equals 679 kilojoules per mole, that's the energy absorbed to break the bonds. Next, bonds formed, 2 HCl bonds each worth 432, so total energy released is 864 kilojoules per mole. Now subtract, 679 minus 864 equals negative 185. A negative value indicates an exothermic reaction, so energy is released. Remember, the formula is energy in minus energy out, and a negative result means the reaction gives out heat. Watch out for these common mistakes. First, when calculating bond energies, always check the number of each bond type in the equation. A common error is to use the bond energy as given without multiplying by the number of bonds. Second, remember that exothermic reactions have a negative H, endothermic positive. Third, on reaction profiles, always label the activation energy as the hump from reactants to the top of the curve, and show the overall energy change as the difference between reactants and products. Finally, always state whether energy is transferred to or from the surroundings. Examiners look for precise language. It's not enough to say heat is given out, say energy is transferred to the surroundings, so the temperature increases. Let's wrap up with a quick recap. Exothermic reactions release energy to the surroundings, cause a temperature increase, and have a negative H. Endothermic reactions absorb energy, cause a temperature decrease, and have a positive H. Activation energy is the minimum energy needed for particles to react. It's the hump on a reaction profile. For bond energy calculations, the formula is energy absorbed to break bonds minus energy released when forming bonds. A negative result means exothermic, positive means endothermic. Finally, remember real-world applications. Hand warmers use exothermic oxidation of iron, sports injury packs use endothermic ammonium nitrate dissolving, and hydrogen fuel cells provide efficient electrical energy from the exothermic reaction of hydrogen and oxygen. Master these concepts, and you'll secure top marks in your exam.